Hello, this is Miss Moore, and today during chemistry we're going to continue discussing types of chemical reactions. Specifically today we're going to talk about double replacement reactions, also known as double displacement reactions. Okay, today's essential question: how are the products of double replacement reactions determined? All right, for today's lecture you need a couple things handy. You need your periodic table and polyatomic ion chart. Also, if you look in your packet, you will find something titled Solubility Rules. Get that out as well. Okay, so double replacement or displacement reactions. Okay, so if solutions of two ionic compounds are mixed, one of two things are happened. You'll either get an aqueous homogeneous mixture or a chemical reaction. Okay, so let's discuss this particular sentence for a moment. First of all, when you have a double displacement reaction, it's between two ionic compounds, okay? And they're going to be in the aqueous state. So aqueous, AQ, means the ions are dissolved in water. Okay, and they're separate ions just floating around. Okay, so what are the two things that could happen? First of all, you could get an aqueous homogeneous mixture. That means your products are all going to be aqueous. Aqueous, let's try that again. AQ, which means basically there isn't a reaction, okay? They're just ions floating around. Nothing really happened. Or you'll get a chemical reaction. When you have a chemical reaction, you can produce a solid, a liquid, or a gas. Okay, and more on that as we proceed. During a double replacement reactions, what's actually happening is that you're exchanging the positive ions between two reacting compounds. The positive ions, also known as the cations, are the metals, right? So another way to think of it is the metals replace the metals. The last way to think about it is the elements from the left side of the line on the periodic table. We're talking about on the periodic table. Switch places, okay? And remember, the guys on the left are the metals. Okay, and so here we have our general formula for a double displacement or replacement reaction. And as you can see, the A and the B are switching places. And the A and the B are the cations because they're written first, so they are positive ions, they are the metals. Okay, so that's generally what happens during a double displacement or replacement reaction. Now let's get into the part that's slightly more complicated. Okay, when a double replacement reaction actually occurs, one of the following is true. One product is only slightly soluble and precipitates from solution. Okay, so basically part of it is insoluble. Okay, insoluble, so you end up with a solid. Okay, the precipitate is a solid. One product is a gas, or one product is a liquid molecular compound like water. Okay, if all of your products end up being aqueous, meaning the ions just are still floating around in the water, that means there's no, ran out of room there. Let's see, that means there is no reaction. All right, hopefully you guys can see that, no reaction. Okay, and we'll get into more detail about that in just a moment. All right, so let's talk about these solubility rules. You can look at yours while I'm going through this. I'm going to be writing things on this. This is a handout. Do not write stuff on this. Okay, so let's try to read through this and see if this makes sense. So if you have ammonium, so any ammonium is NH4, and any group 1A element like hydrogen, lithium, sodium, potassium, etc. What does that tell you? Well, all of those are soluble. Soluble means it's dissolvable. It dissolves. which means it dissolves in water. It means it's aqueous. Okay, AQ. Okay. Nitrates, that would be your NO3s, chlorates, your ClO3s, perchlorates, these are all polyatomics, and your acetates. All of these guys are soluble. Again, dissolvable, which means AQ. Okay? Halogens. The halogens are the group 7A, fluorine, chlorine, bromine, etc. So they're mostly soluble. Fluorides, not so much. They're mostly soluble unless they're bonded with silver, lead, or mercury. In that case, they become insoluble. Okay, so let me define insoluble while we're here. Insoluble means does not dissolve. This is when you're getting your solid or your precipitate. Okay. All right. Then we have the sulfates. Most are soluble, meaning most will give you an AQ, aqueous, except when bonded with calcium, strontium, barium, lead, and mercury. Okay, hydroxides. The hydroxides are the OHs. Most are insoluble, meaning most will form a solid, except for when bonded with ammonium, group 1A metals, and also barium, calcium, and strontium. Okay, then we've got a whole bunch more polyatomics here, the phosphates, carbonates, chromates, oxalate, and silicates. Most are insoluble, meaning they'll form a solid, except when bonded with the group 1As and the ammoniums. And then we've got the sulfides and the oxides, so that's like the S and the O. Most are insoluble, meaning they'll form a solid, except when bonded with, again, ammonium group 1A and most group 2A metals. Okay, so whenever you're performing or whenever you're doing a double displacement reaction, we're going to have to refer back to this chart to see whether or not the reaction happened. Okay, if all of your products are aqueous, then the reaction didn't happen. Okay, let's go over the steps to write or complete a double replacement or displacement reaction. The example we'll be using is Na2S plus CaCl2. And one thing I want to point out is these are both aqueous. That's one of the requirements for there to be a double replacement reaction is that your reactants need to be aqueous or dissolved in water, need to be in solution. Okay, so the first thing you want to do is, just like we did for the single replacement, you want to figure out the charges on all of the ions in the compound. Okay, so we have Na2S, and I'm going to go ahead and put that aqueous, even though it doesn't matter for balancing, it does matter for whether or not the reaction occurred, plus CaCl2, aqueous, and that's going to give us something. All right, so Na has a 1 plus charge, sulfide has a 2 minus charge, calcium has a 2 plus charge, and chloride has a 1 minus charge. Okay, so what's going to happen here is the sodium and the calcium, remember the positive switch places, so these two guys want to switch places. All right, so now let's write the skeleton equation, write the products. Okay, so what's supposedly going to happen is that the calcium, Ca, is going to hook up with the S, and the sodium is going to hook up with the Cl. And we can put the charges back. Calcium is a 2 plus, 2 minus, 1 plus, 1 minus. All right, now make sure that all ionic compounds are neutral. So we have 2 plus and 2 minus for the calcium and the sulfide, so that's good. And 1 plus and, oh, the Cl got cut off. Put it back. And 1 minus for the sodium chloride, so that's good. These were already neutral, so we can get rid of all of those. So now all our ionic compounds are neutral. Okay, so now we got to do some thinking. We've got to determine if the products are aqueous, solid, liquid, or gas using the solubility rules. So let's, we can put back our reactants. We have Na2S, which is aqueous, plus CaCl2, which is also aqueous. All right, so now let's look up CaS. Okay, so let's jot that down so we don't forget what we're looking for. We have CaS, and so calcium and sulfides. Well, sulfides right here, sulfides are insoluble, which would mean a solid, right? Except with bonded with group 1A and 2A metals. Well, calcium's a group 1A metal. No, it's not. Group 2A metal. So it's going to be aqueous. All right, so let's stick that in there. So now we know we have CaS, which is aqueous, plus, let's check out NaCl. All right, let's check NaCl. Well, Na is a group 1A metal, and it says all group 1A metals are soluble, which means AQ. So we have NaCl. Oh, I'm out of room. All right, let's put that down here. Plus NaCl aqueous. So aqueous, remember, means everything dissolves, is dissolved in water. The ions are just floating around. So did a reaction occur? No. So after all that work, we've come to find out there was an R. And now you balance the equation, which we don't need to do because it's an R. So that's how you do double replacement or displacement reactions. We will, of course, try a few more. Okay, let's try a practice problem. I'm going to suggest if you would please try this on your own first and then hit play and see how you did. All right, so cadmium is not a group 1A, 2A, or 3A metal, so we have to go backwards to figure out its charge. So we have Cd and 2 Brs, which each have a 1 minus charge. Gives us a total of 2 minus, which makes cadmium a 2 plus. And we know that bromine is a 1 minus. Sodium is a 1 plus, and sulfate is a 2 minus. Okay, so in this particular example, we're going to have cadmium and sodium. We're going to switch places. So we'll end up with, let's see, sodium bonded with bromine and cadmium bonded with sulfide. Okay, and now we check the charges. We know these are all good, so we can get rid of that. So sodium and bromine are neutral, and cadmium and sulfide are neutral. Okay, so now we need to check and see solid or aqueous. So NaBr, Na is in group 1, bromine's also a halogen, and they're soluble. Soluble means aqueous, right? So he's aqueous. CdS, S is a sulfide. Most are insoluble, except when bonded with ammonium or group 1 or 2A metals. Well, cadmium is not a group 1 or 2A metal, so he's going to be a solid. So now, this time we have a reaction. All right, so the next thing we need to do is balance. Let me rewrite this. We have a little bit more room to work here. So we have CD Br2 aqueous plus Na2S aqueous produces NaBr aqueous plus CDS solid. Okay, now as we're going through balancing, you don't need to worry about the aqueous and solid. They have nothing to do with the actual balancing. All right, so we have CD, Br, Na, and S. All right, on the reactant side, we have 1 cadmium and 1 on the product side. Bromines on the reactant side, we have 2 and 1 on the product side. Sodiums, we have 2 and 1. And sulfurs, 1 and 2. All right, and then to fix this, to balance it, cadmiums are good. Bromines, well, if I put a 2 right there, I now have 2 and 2. And that fixed it. So there's our answer. And that's it for today.